Truman's left the room now. Okay, so this is our first flipped lesson for a chapter in the textbook. So we're going to start with, this is chapter 1, lesson 1. You can follow along in your textbook, but we're going to start talking about motion, and everything we're starting from now until the building of your coasters is really all going to be focused around how objects move, the forces that cause motion, and then how to measure those forces. And we're going to start today simply by just describing motion. So, as Truman did so eloquently say, it is fairly simple. Motion is basically defined as if an object changes its position relative to another object or in relation to another object, that object is considered in motion. Now, we see things move all the time and we don't often think, well, how do we know they're moving? You know, how do you know, like, your hand is moving? Just move your arm up and down. How do you know that's moving? Or if someone walks across the room, how do you know they're moving? Well, we can tell that an object is in motion because our frame of reference is what is behind your arm or behind the person. This person or this car is moving relative to another object. And you can see the position change, and then you know that the object is in motion. The point or object that you are using to compare to help determine an object's motion is called a reference point. So as Truman was walking across the room, I could tell that he was moving because my reference point was the light behind him. So if you just take a moment and move something, move your arm, move your head, how do you know that that is in motion? You are comparing that to a reference point. Now, reference points can be stationary, which is fairly simple. You know that something is moving if your reference point is stationary. But you can also have moving reference points. Moving reference points can be, you might have to take a moment to determine whether or not an object is in motion. And I don't know if you've actually had this experience, but I have. In the cathedral parking lot, actually, sitting in my car is on but not driving, and someone next to me will start to pull forward. When that person next to me is pulling forward, you can get the impression or feel as though you are moving backwards even though you are not in motion. When you're using a reference point that is in motion, that can lend itself to a little bit of confusion. Another example of this is using clouds in the sky that are moving as your reference points. How do you determine if a hot air balloon is in motion, or you know, a bird, if you're using another object that's also in motion? So one of the more, it tends to be a little bit more of a confusing part of this is relative motion. So when you're comparing, like asking yourself, am I in motion relative to something else? So I'm sitting on a couch right now, you might be sitting at your desk. Are you in motion relative to the chair? Am I in motion relative to the couch? I'm sitting here, my answer would be no. In comparison to the chair, I am not in motion. Now, ask yourself the same question, my couch and your chair, we sit on the planet Earth. Are we in motion relative to the sun? Now, I'm sitting on this chair and I am not moving, so I would say that I'm not in motion relative to the chair. But I am in motion relative to the sun, because I am on a planet that is revolving around the sun. So when we talk about motion, this is the thing. So, you know, is the sun in motion relative to the Milky Way galaxy? Now, you would say the sun is not moving, but in reference to that galaxy, it is rotating around a galaxy. So just ask yourself, yes, am I in motion relative to this chair? No. But am I in motion relative to the sun? Yes. Now, measuring motion. We're going to spend a lot of time measuring motion this week, in fact. And so this is going to be the first time we talk about SI units this year. We've talked about this in the past. We've talked about using the metric system. The SI units is the International System of Units. And we didn't use a lot of units in life science and didn't really talk too much about this after our first couple of weeks. But in physics, with a lot of measuring, we are definitely going to be talking about these units. What I really want you to focus on are these base units up here, and then we're going to use some of these derived units. But the base units for SI are, for length, we're going to be using this week is the meter, mass, kilogram, and time second. Those are the things we're going to be using this week. So when we're asking to measure our motion, we are going to be using this scientific system of measurement. So we're not going to be measuring in inches or pounds. We're going to be measuring in meters and kilograms and seconds. Now these are the base units: length, mass, time, current, temperature, amount of a substance, and luminosity. There are some derived units, meaning units that are combined. So the first ones we're going to be working with this week are right here: speed and velocity, are meters per second. And so in the next couple of slides, you're going to see what I mean by those derived units. The next couple of videos we're going to be doing are going to be using the metric system and converting units, because you might be measuring things in centimeters and millimeters and meters, and even, probably not, but maybe even discussing things like kilometers. So just for our purposes now and in our upcoming lab activity, just know that the system of units that we're going to be using is called the SI unit, and we are going to be working with our base units and then deriving some units from there. This week we're going to be talking about speed. Okay? So if we're talking about an object is in motion, we can measure a lot of things about that object in motion. And the first thing we're going to measure is speed. We're going to also measure acceleration and momentum and forces on that object and friction. But right now, we're going to start simply as measuring its speed. So speed is defined as the distance that an object moves per unit of time. Okay? So how fast you're moving, it's how much distance you are covering in a certain unit of time. We say that speed is a rate, and we're going to deal a lot with rates this year. A rate tells you the amount that something occurs or changes in a specific amount of time. So we're not just saying you moved 10 meters. Okay, that might tell me your distance, but it doesn't tell me your speed, because I need to know how fast you did it, how much distance did you cover in a specific unit of time, and that gives us our rate. Okay. We'll also talk about velocity and acceleration are also rates. How much something happens, how much you speed up and slow down, how quickly you change direction, or how much distance you cover, all per unit of time, which makes that a rate. This is our first equation in physics, of which there are many. When we're talking about measuring motion, we're going to be dealing with some physics equations and units. And our first one is speed. Speed equals easily distance divided by time. Okay. Now, this is our unit. Our unit is meters per second. This is our first derived unit. So distance is measured in meters. That's length. Okay, so length is measured in meters. That's our distance. And time, we saw on our previous slide, is measured in seconds. So distance divided by time is meters per second. This week, we're going to be working on a lab activity where you are recording one another's time and altering your speed and covering different distances and recording time. So you'll be pretty familiar with how to use this equation. But always remember units. In physics, what you are calculating is useless to me or to anyone unless it has units. So we'll start simply with distance. Speed equals distance divided by time, and the unit for that is meters per second. Here's an example. So a football field is about 100 meters long. If it takes a person 20 seconds to run its length, how fast were they running? Okay, so if speed equals distance divided by time, then this could simply be written as 100 meters divided by 20 seconds. Okay, that is equal to 5 meters per second. So this person was running 100 meters in 20 seconds. They were covering 5 meters per second. The crazy thing is Usain Bolt's 100 meters in under 10 seconds means he was covering more than a meter in a second, which is kind of mind-blowing. Okay, pitcher's mound. The pitcher's mound in baseball is about 85 meters from the plate. It takes 4 seconds for a pitch to reach the plate. How fast was the pitch moving? So 85 meters divided by 4 seconds equals about 21.25 meters per second. Okay, so that pitch was covering 21 meters for every second that it was moving. All right, I'm going to stop there. A little over time. Sorry, you can blame Truman for that. Tomorrow we're going to be working on some examples. You have a set of notes to complete with some examples on those notes, and we'll be calculating one another's speed tomorrow. Thank you very much.